In this video, we're going to take a look at electrolytic cells. So what is an electrolytic cell? Well, an electrolytic cell is based on a non-spontaneous redox reaction, or it has a delta E naught that is a negative value. And so in order to drive this particular cell to work, it requires an external power source. So some sort of battery. If you remember and recall from previous science courses, our battery is represented like this. And so what it does is it does the opposite of what a voltaic cell does. It converts electrical energy, so it takes this energy from the battery and converts it into chemical energy. So it's creating our chemical reaction for us. Now, a couple things to note about electrolytic cells. The anode is still where oxidation occurs, and the cathode is still where reduction occurs. In terms of charges, the anode's positive and the cathode's negative. So this is more based on our electrical source than it is on our energy flow. And our electrons still flow from anode to cathode. And one of the big main differences for this sort of cell is that it's all done in one electrolyte solution. So it's just a single cell where you have your two electrodes in there. Generally, your anions or your negative ions are being attracted to the anode, and your positive cations are being attracted to your cathode. So there are a few scenarios we need to take a look at in terms of electrolytic cells and doing the diagrams. So let's take a look at some of those examples now. Now let's start off with, and very typically, a lot of the electrodes we use in electrolytic cells are something that is inert. So something like platinum or carbon or graphite is not likely to react. And so they make really, really great electrodes. So looking at this then, if we take, for example, our electrolyte as potassium bromide in the liquid states, we would say that this is in the molten state. And so if we're trying to figure out where the ions are going within this electrolytic cell and what's happening, we need to consider and take a look at potassium ions and bromine ions. And these are both just in the liquid state because there is no water in the molten state. So if we take a look at our chart of redox potentials, and we locate both of these on the chart, potassium ions are way up at the top here, and bromine ions are way down at the bottom here. So you can see the difference. This is a non-spontaneous reaction. If we were to calculate the E naught from our values, it would give us a negative value as well. So what's happening here is the potassium ions are going to undergo, since it's our oxidizing agent, is going to undergo reduction. And so that's going to happen at the cathode. And our bromine ions are going to undergo oxidation, and that is happening at the anode. So let's go put these on our diagram. So in our diagram, let's just pick one of these as the anode, the other one as the cathode. And remember that oxidation happens at the anode, reduction happens at the cathode. So we do want to just jot down the reactions that are happening for each. So potassium ions and electrons are forming solid potassium at the cathode. And then at the anode, bromine ions are reacting to create liquid bromine and electrons. So showing that in our solution here, I'm just going to show bromine ions and potassium ions. the potassium ions are going to be attracted to our cathode. And so then that's where this reaction here is going to happen. The bromine ions are going to be attracted to our anode, and that is where our oxidation half reaction is happening. We also want to put in the charges here. So we got a positive and a negative charge. And then let's just put in our battery, and we're going to show the electron flow going this way. Okay, so that's pretty much everything that needs to go into a electrolytic cell diagram. So it starts to get a little bit trickier when you start adding in additional things into either your electrodes or your electrolyte. So looking again, if we take another example with an inert electrode, so something like platinum carbon or graphite again, but let's now look at potassium bromide that is aqueous. So we have to consider potassium and bromine ions, but we also have to consider water. And so sometimes water can be either oxidized or reduced depending on where it sits in relation to our other ions. So let's go look at our table to see where we're at. Now looking at our table, we find potassium ions up here, water's on this side, bromine ions, and then water's on this side again. So what that means is when we have potassium bromide that's aqueous, our water is now our strongest oxidizing agent, and our bromine is our strongest reducing agent. So that means water is going to undergo reduction at the cathode, and bromine's going to undergo oxidation at the anode. So let's put this into our diagram very quickly. So we've got our battery, we've got our anode, our cathode, positive charge, negative charge. The bromine ions are still being attracted to our anode, and so it will undergo oxidation there, and we would have our oxidation reaction of the bromine reacting to give liquid bromine and an electron. And then at the other side, it's our water that's being attracted here, and it's going to create hydrogen gas. So it's actually going to create some bubbles of hydrogen gas. So if we were to write out the reaction, taking it from our table, we'd have liquid water, we would have an electron, and that's going to give hydrogen gas and hydroxide ions. Okay. So a little bit different, and you do get different products just by creating an aqueous solution of potassium bromide. Now, our last example, we're going to throw in copper electrodes into the mix. So these are both copper. And we've got our potassium bromide in aqueous solution. So we now need to consider the potassium ions, the bromide ions, water, and the solid copper from the electrodes. So let's take a look at our table and figure out what reaction is actually happening here. Looking at our table, if we look on the oxidizing agent side, we got our water here and our potassium ions here. So our water is still our strongest oxidizing agent, so it will undergo reduction. And then if we look on the other side, our bromide and water are there, and our copper solid is right here. So our solid copper is actually higher in the table than the bromine and the water. And so that means that this is going to be our strongest reducing agent. So the copper itself is actually going to undergo oxidation. And with our water, strongest oxidizing agent, that's going to undergo reduction. So finally, putting this onto our chart here again, we got our electron flow. If we're going to make this the anode and the cathode, we got positive charges, negative charges. And then at this particular electrode, the solid copper is being oxidized. And so what's happening is we have solid copper being turned into copper 2 plus ions and 2 electrons. So this copper is breaking down into copper 2 plus ions, which means eventually over time, this electrode is going to get eaten away and eventually disappear if we let this go on forever and ever. The reduction half reaction is our water one. So we've got water and an electron. It's going to create that hydrogen gas again and hydroxide ions. Okay, so our water is now being attracted here, and it's going to again create those bubbles of hydrogen gas. So I think that's about it for our diagrams. You should also, for all diagrams, create an overall reaction and list that underneath. I haven't done that for each of these, but try that out for yourself and take a look at that. But it's really neat in terms of what you're putting in an electrolytic cell, whether it's the actual electrolyte that's reacting or whether it's something else that's reacting. And it can change very drastically just by tweaking and changing a couple of little things. Finally, just want to mention really briefly here that electrolytic cells have some really great uses. One being electrolysis is used to produce pure elements from compounds. So, for example, if we did the electrolysis of water, we could produce pure hydrogen and oxygen gases. Another really neat use, and you'll see this in a future video, is electroplating. And so this is creating, like, for example, gold or silver plated jewelry. So you can plate different metals onto a particular object. Really neat. That's it then for this video. Let's move on to our next task.